Okay, so Bismillah Rahman Rahim. Let's start the last part of the topic. The topic is dam-free vibration systems. So we are left with two problems. So we will solve two problems in this lecture, and in the next lecture, inshallah, we will start the next topic, which is dam-forced vibrations. So let's start with the two numericals which we are left in the last lecture. So first we will attempt the example 2, and in this example, so what it says is there is a simplified model of the car shock absorbers. If you just imagine or you have seen the car shock absorbers, they consist of a spring and a damper. Generally what happens in many cars, you have a damper inside a cylinder assembly. Just to draw the outline of the damper that is used, so we have this, we have a rod. That rod has a piston in it. There is a lower part which is attached to the chassis of the car. The upper part is attached to the car body, and over that damper we have a spring coil. This is called McPherson stud suspension. In other cars, like in case of Wits, you have a separate spring and damper attached separately to the body. So it depends upon the company which is manufacturing the car, but generally both, if it is the spring is coiled over a damper or if it is placed separately, both have the parallel combination, both acts in the same way. So this is what generally the car manufacturer uses this scheme to install the shock absorbers in the car. Now, a numerical says a portion of an automobile suspension consists of an elastic spring. As you know, you have seen these springs, and a viscous damper. Now, in cars, they have used a damper which is called piston cylinder dashboard damper, and these dampers generally use a shock oil, which is, I think so, 10W grade. So these generally classified as the viscous dampers. So he says if the ratio of K over M is 40, which is generally true for most of the cars. Why? Because generally for the car with the mass of roughly 1 tons, the spring generally has a stiffness of nearly 40 kilonewton per meter. So if you divide this, so this K over M generally is 40 kilonewton is nothing but 40,000 divided by 1 ton is 1000 is roughly 40. Now it's not exactly 40 in all cars, it generally ranges from 30 to 45. Okay? So average value you can take it is about 40. In case of bikes, generally the mass is around about, including the passenger, is about 200 kg, and the spring that has been used is roughly about 20 kilonewton per meter. So if you just divide it, you approximately get, I don't know, there's some value closer to this, but it can vary. It can be some 25 as well. But anyhow, the ratio is very important while designing the shock absorbers of the car. He said determine the allowable range of the ratio C over M. So we're interested in C over M, clear? Such that any oscillation that occurs will decay by a factor of 95% within one cycle, which generally says, this is a very important concept. It says if it starts at let's say 100%, so in the next cycle your 95% of the amplitude should decay. So if I let this take as x0 and this is x1, so if this x0 is 100% and 95% should decay in one cycle, so this must be 5%. I again repeat. So it says determine the allowable range of the ratio C over M, so that any oscillations that occur will decay by a factor of 95% within one cycle, which means that if cycle starts at this point, and end at this point, so in the next cycle you have only 5% amplitude is left. So by seeing this, we say x0 is nothing but 0.95. If we sorry, not 0.95, sorry, is actually 100%. which you take numerical value as 1, and x1, which is the amplitude of the next cycle, is 100 minus 95, which is 5%, and this can be written as 0.05. So although the absolute values is not given in the numerical, you just say take it 100% as a one factor. So whatever the x0 is, x1 is 95% less than that particular. Okay. So we are interested in finding the C, and you know that C is related to zeta. So if we if we somehow find the value of zeta, then we can put this to get C here. And if I just simplify this relation, so C over, and you know CC is 2 m omega n. So C over m is nothing but 2 zeta omega n. So this is what we are interested in. Clear? Now omega n is known, which is k over m, and is known it's 40 as given in the numerical. The value will come out to be if just take this value, I just find that value. Okay, using a calculator. So if I just find the value of come out to be 6.32. So it will come out to be 6.32 radians per second. So now we are interested in find, if we know the zeta, then we can find the value of C over m. Now for zeta, as you know, we have given the amplitudes. You can find the delta first. So delta is nothing but 1 over n natural log of x naught over xn. Here, because you have one cycle, so n is equals to 1, so you get 1 natural log of x naught is 1 and x1 is 0.05. So delta is nothing but, you should take natural log of 1 divided by 0.05. What you get is 2.99. So you get 2.995. This is the value of zeta. And if you know the relation that we are using, we have derived in our modeling of the logarithmic decrement, so zeta is nothing but delta over under root 4 pi square plus delta square. So you put the value of delta in the equation, so you get 4 pi square plus 2.995 square. So you get the zeta is equals to 0.43, which indicates the system is underdamped. This is a normal value of the most dampers of the cars, zeta value, which is roughly ranges from, in most of the cars, the zeta value ranges from 0.2 to 0.5. This is for the Culters, for the Corolla, for the Honda. So this value come out to be true, and most shock absorbers are underdamped systems. Now we know what the value of zeta is. So just put C over m is equals to 2 zeta omega n. So 2 zeta is 0.43, and what is omega n? That is 6.32. So what you get is, if you multiply this, you get the value of C over m come out to be 5.44, and the unit is per second. Clear? Or in other words, you can call it, because its unit is Newton second per meter per kg. Either can a unit of per second or Newton second per meter per kg. Okay, we're going to start the next numerical, and next numerical says that you have a spring and a damper. So this is a damper, this is a spring, and it's a mass that is moving with the velocity of 15.24 meter per second, and it's engaged a spring and a damper. So the numerical says determine the maximum displacement of the piston. So it says when let's say you have a spring here and this is the damper. So he says when the mass actually attaches this a platform on a plate, how much deflection, maximum deflection this mass can take. So we are interested in finding, let's say if that's moved toward this point, so this is x max, so we are interested in x max. Okay? And secondly, how much time will it take to reach the maximum displacement. This is our purpose for the numerical. Now for this sake, first of all we have to derive the response of the system. Why? Because without the response of the system it's very difficult to find the maximum displacement, because you know, if you derive the displacement equation, only then you will be able to solve the system. So first we will see to solve the system, we first use the basic relation of underdamped. Okay, now we don't know whether the system is underdamped, critically damped or overdamped. So let's say we first see whether the system is critically damped, underdamped or overdamped. So zeta is equals to C over Cc. Now C is given, which is 1.75 Newton second per centimeter. So if you convert centimeter into meter, so that is nothing but 175 Newton second per meter. Okay, this is C, and Cc is 2m omega n. Now this is 175 divided by 2 into 2 into what is the mass? Mass is 4.53 kg into the omega n is nothing but under root k over m, and k here is 350 Newton per centimeter, which is again 350 into 10 power 2 Newton per meter, divided by m is 4.53 kg. If you solve this, you come out to be so zeta is nothing but 0.22. If you solve the above equation to get, so it's an underdamped system. So if we have derived it's an underdamped system. Now we will use our equation, which is x of t is equals to E minus zeta omega nt C1 sine of omega dt plus C2 cos of omega dt. Okay, now we have to use the initial conditions. Now look at the initial condition. Now because mass is moving with a velocity and it hits the mass, so whenever there is an impact, you only have the initial condition of the velocity, which is v0, which is 15.24 meter per second. Okay, I am again repeating, because this mass is accelerating and hits this platform, which consists of a spring and a damper. Now because you have not given an initial displacement, but only the impact. Now when this mass with a certain velocity hit this platform, it imparts a velocity to the system, which is considered as the initial velocity. So there is no displacement here, so this is equals to 0. Now to find out C1 and C2, again just as we have done in the previous case, we have to use the initial conditions. So first putting the values of E, and what is zeta is 0.22, and omega n is 350 into 10 power 2 divided by 4.53. This is what our omega n is. The value come out to be 19.3. So minus 19.3 t C1. And what is omega d? Omega d is nothing but omega n under root 1 minus zeta square. So omega n is, as we have find out, is actually equals to 87 point, if you find out omega n, it is 87.9. 1 minus 0.22 square, you get 85.7 radians per second. Clear? This is what omega d is. So C1 sine of 85.7 t plus C2 cos of 85.7 t. Clear? Now use first the first initial condition. So x of 0 is equal to 0 is equal to this goes to 1, C1 this goes to 0, and this cos goes to 1. When we put t is equals to 0, so you get C2 equals to 0 from the first equation. Your C2 actually goes. For the second case, you have to take the derivative of this equation. So taking the derivative using the product rule. So I'm just writing the derivative. Plus e minus 19.3 t, and if we take the derivative, second case, this will come out to be 85.7 C1 cos of 85.7 t minus 85.7 C2 sine of 85.7 t. Okay, if you just put the value of x dot of 0, which is 15.24, 0, this goes to 1, so minus 19.3 times, just write with another color, this goes to 0. The C2 is 0, so this term whole goes to 0, so you write 0 here, plus this goes to 1, so 85.7 C1, and this goes to 1, so 1 here, minus 85.7 C2 is 0, so everything goes to 0. So what you end up with 15.24 is equals to 85.7 C1. So C1 is nothing but 15.24 divided by 85.7, and that come out to be 0.18 meter. So if you put the value in the displacement equation, so this become equals to E minus 19.3 t. C1 is 0.18 sine of 85.7 t. So this is your solution. Now we are interested in finding the maximum displacement. Okay, so this is the final solution of our system. So we are interested in finding the maximum displacement. Now if you remember from the first lecture, we know that we have three terms to measure the vibration. One is displacement, one is velocity, one is acceleration. And if I draw these curves, response, so where the displacement is 0, so we know that where the displacement is maximum, velocity is 0. So the trick is, if we take the derivative of this equation, so x dot of t is equals to, if we take the derivative of this equation, so this becomes, again we have to use the product rule, so 19.3 e minus 19.3 t into 0.18 sine of 85.7 t plus e minus 19.3 t 0.18 into 85.7 cos of 85.7 t. So x dot of t is equals to, you just simplify this, what you end up is, because e minus 19.3 is common, if you take common, 19.3 is multiplied by 0.18, you get minus 3.5 sine of 85.7 t plus, if you multiply 0.18 for 85.7, you get 15.4 cos of 85.7 t. So the trick is, if we put x dot of t equals to 0 and try to find the time, so this time, because this is a time equation, this is time axis, sorry. So if you find this time where velocity is 0, that will get the maximum displacement, and same is the case for the acceleration. So I am again repeating, find out the displacement equation, put the derivative to get the velocity, and if you put the velocity equal to 0, you somehow get the time at which the velocity is 0. So then you actually get the time at which the displacement is maximum. So 0, and now we have to put, now you don't have to put time is equal to 0 here. This time is not equal to 0, the velocity is equal to 0. So we are interested in finding the time. So this is the whole, so just again don't write it. This is the same equation above. Now you see the equation has two parts. One is this part, second is this part. You know, for any t, e minus 19.3 t cannot be 0. So we have only possibility, that is minus 3.5 sine of 85.7 t plus 15.4 cos of 85.7 t is equal to 0. I am again repeating, the equation has two possibilities. The first, the e minus 19.3 t is common. So if you put any value of t starting from 0 to whatever the value is, you cannot get this term equal to 0. But the only possibility that exists within the bracket, which is this term is equal to 0. Now using this relation, you can actually solve this to get your time. So I just solve it. So you just take this on the other side, this term on the other side. I just write on the new page. So sine of 85.7 t divided by cos of 85.7 t. You just take on the other side, take cos in the denominator, you get 15.4 divided by 3.5. So you get 4.4. Clear? Now remember, okay, so if you take 85.7 t, so this is nothing but tan of 85.7 t equals to 4.4. Clear? So 85.7 t is nothing but tan inverse of 4.4. So just take tan inverse of 4. You get? Okay, so t is, so tan inverse of 4.4 is 1.35, provided your calculator is set to radians. This is what you have to remember, because we are working with radians. You see, your omega n is in radians per second. So we are calculating in radians. So you have to convert your calculator into radians. Otherwise, your vehicle will be wrong. 85.7, you get a time of 0.015 seconds. This is the time to reach the maximum displacement. So if you put the time in this equation, displacement equation, so you get x of x max equals to e minus 19.3, and time is 0.015. Clear? you get into 0.18 sine of 85.7 into 0.015. Again remember that this is in radians per second, so and this is seconds, so the angle will come out to be in radians, so you have to convert your calculator into radians, otherwise I'm again repeating, your numerical will goes wrong. So if you solve this, and very easy to solve, so x max is equals to 0.13 meter or 13 centimeter. This is the maximum displacement that your mass with the mass of 4.53 kg moving at a speed of 15.24 meter per second hits the platform containing the spring and a damper. It can reach to a maximum displacement of 13 centimeter in 0.015 seconds. Now the second way to do this, if you remember this, if you take the response, so it will, when the mass will hit the spring, so this mass is moving and you have a spring and a damper. So when it hit this, it starts from its mean position, which is 0, reaches to the maximum value, and you know, for the maximum value this angle is pi by 2. The trick is, if you you know the solution, which is x of t is equals to e minus 19.3 t into 0.18 sine of 85.7 t, and you know this is nothing but, this is nothing but theta. So if your theta is pi by 2, then your sine of theta is equals to 1. So so it means that, so as the maximum displacement occurs when the angle is pi by 2, and you know that from your previous understanding. So you can now say from above equation that 85.7 t is nothing but is equals to pi by 2. So for that case you get time is equals to 0.018 seconds. So it's slightly larger than, the answer is very, there's a large difference between previous case, and if you find using the same time, if you find the maximum displacement, so it is 0.127 meter using this relation. Now if you just see that, you will see this this method is quite easy as we have done the previous system, but this is tricky. This is tricky. Why? Because if you have two initial conditions, then you have another term, you have a cos term here, then you cannot use the second method. I am again repeating, if you have two initial conditions, that is the displacement as well as velocity, you cannot use the second method which I explained, this method. This is only can be used